This is example 9.1 in the Smith Van Ness 8th edition textbook. It's a refrigeration example. We've got a refrigerated space is maintained at minus 20 degrees Celsius, and we're told that cooling water is available at 21 degrees C. The refrigeration capacity is given to us at 120,000 kilojoules per hour. We are told that the evaporator and condenser are sufficient size that a 5 degrees C minimum temperature difference for heat transfer can be realized in each. And we're told the refrigerant is R134a. We're asked to calculate the value of the coefficient of performance for a Carnot refrigerator, and then calculate the coefficient of performance and the mass flow rate of refrigerant needed for a vapor compression cycle, figure 9.1 in our book, if the compressor efficiency is 80%. So I've got the compression cycle given here. This is the same as figure 9.1 in your textbook. It's just flipped around a little bit because I like to see things going clockwise. But we've got our evaporator, compressor, condenser, and expansion valve. The first thing that we need to think about for this problem, and by the way, I'm going to skip the Carnot calculation and save that until last. Let's look at the actual cycle itself. The first thing we need to think about is what are the temperatures of the cold reservoir and the hot reservoir, TC and TH, or you could think of it as what are the temperatures that the refrigerant is going to boil off at in the evaporator, which is TC, and that the superheated vapor is going to condense at in our condenser, that is TH. And this problem statement gives you the information a little bit more indirectly than maybe what we're used to saying. But we're told that the refrigerant space, so whether or not this is a compartment of a freezer or maybe a freezer room, it needs to be maintained at minus 20 degrees C. So let's think about the cold side first, minus 20 degrees C. And then it says that we must maintain a 5 degrees C minimum temperature difference for heat transfer to occur. So what this is saying is that our refrigerated space has to be minus 20 degrees C. Now, what that means is that the evaporator should operate at a colder temperature. So that is true for all these refrigerator heat pump cases. Our evaporator should operate when we're trying to pump heat from a cold reservoir to a hot reservoir. Our evaporator should be colder than the space that we're trying to maintain at a cool temperature. So what this means is that if our room temperature of our, say that this is a freezer room, storage room, has to be minus 20 degrees C, our evaporator needs to be colder than that at minus 25 degrees C. So that's what that's saying. We have to be able to cool the air, we need a finite temperature difference to maintain heat transfer. So that's the explanation for TC being minus 25 degrees C. And we're going to put things in Kelvin because we work with second law. Same thing for the condenser. Now, what we were told is that we have cooling water available at 21 degrees C. And they don't say this in the problem, it's a little unclear, but that's for the condenser side. So remember, in the condenser, we take superheated vapor from stream 3, we cool it down to a saturated vapor, and then we condense it to a saturated liquid. That needs to be done by the air that is available to us, or I should say the fluid. In this case, the fluid is not air, which we would normally think of for most refrigeration or heat pump or air conditioning type of applications, but we have water that's available to do that. And that can be an advantage because water gives us more efficient heat transfer, and so theoretically our condenser should be pretty efficient and a small size. So if the water is available at 21 degrees C, that means that our condensation needs to take place at a higher temperature. So TH is going to be higher than the environmental temperature by 5 degrees C, and so that will be 26 degrees C or 299.15 Kelvin. So that is the first thing that I would do in figuring this out. We need to figure out what our condenser and evaporator temperatures are going to be. Remember, this is going to be saturated liquid, or sorry, vapor condensing to saturated liquid. So that, once we know the temperature, we can specify the pressure on this high side, and then this is going to be saturated liquid evaporating to saturated vapor. That will enable us to specify, once we know the temperature, that will enable us to specify the pressure on the low side. And then of course we have saturated vapor coming out of stream 2. It's being compressed to a superheated vapor. Then it gets cooled, condensed, and then flashed through the throttle valve with an isenthalpic process. And we will start looking at each one of these steps as we solve the problem. Now, the first thing that I usually do when doing these refrigerator problems, I like to set up kind of a stream table so that we can keep things organized. And so I've got the TC and the TH values. And so, as I mentioned, the first thing that I would do is I would figure out what the low pressure side pressure is and what the high pressure side pressure is. And so the low pressure side, that's going to be streams 1 and 2 in the evaporator. The temperature of our saturation condition is 248.15. And so what we do is we look up, and you can use either a saturation property table or you can use the NIST chemistry webbook online properties to look up the saturation pressure at 248.15 Kelvin. That's 1.064 bar. We do the same thing with a condenser. We go to either our textbook, we look up the temperature of 26 degrees Celsius or 299.15 Kelvin, or we go to the saturation tables in the NIST chemistry webbook, and we get a pressure of 6.8543 bar. So now we know the pressures that are in stream 1 evaporator, stream 2, that's the low pressure, and stream 3. The high pressure is 6.854, same here in the condenser and in stream 4. So those are our pressures. So we can summarize this information, and again I think this helps just with the general organization. We are now numbering our streams 1, 2, 3, and 4 according to this diagram that we have. Stream 1 is a mixture of saturated liquid and vapor. Stream 2 is saturated vapor coming out of the evaporator. Stream 3 coming out of the compressor, that is a superheated vapor. We know the pressure, we know it's superheated, but we don't know the temperature yet. That's one of the things we'll need to calculate. And then stream 4 is the condensed liquid that's coming out of the saturated liquid coming out of the condenser. We know what the pressure is and we know what the temperature is. So now we can start solving this problem, and the question is, well, where do we start? And by the way, for this problem, the textbook only asks you to calculate a couple things. We're going to calculate everything, all the work, all the heat, as well as the mass flow rate and coefficients of performance. Well, if you do a degree of freedom analysis to figure out where you can start with the calculations, probably the simplest place to start would either be at stream 4 going to stream 1, because we know the conditions of stream 4, we know the pressure of stream 1, and we know this is an isenthalpic process. And so the combination of our material and energy balance gives us 0 degrees of freedom for this. We also have the same case with our compressor, because remember, we're told that the compressor efficiency is 80%. So we will do an isentropic calculation for the compressor, and using that isentropic assumption, we will have 0 degrees of freedom there. I generally prefer to start with a compressor just because there's more calculations, and I just like starting early and working around the process in a clockwise fashion. So we can start with either one of those, but let's start with a compressor, and we are going to use our standard concept of isentropic efficiency. So for compressors, standard assumptions are that we have steady state flow. They are adiabatic in that the heat losses are negligible compared to everything else that's going on. Also, we have negligible changes in kinetic energy and potential energy. So given these assumptions, the energy balance reduces to the work is equal to the change in enthalpy over that compressor. And of course we can add in the mass flow rate if we want to get our work from kilojoules to kilogram to, say, kilowatts. So we'll approach this like we solve all our other compressor problems. We'll assume isentropic operation. We'll calculate the Once we calculate the isentropic work, then we'll use the efficiency to calculate the real work. And because we want the actual conditions of stream 3, we will use our energy balance to back calculate in the property tables to back calculate the stream temperature of, or the temperature of stream 3. So let's start with stream 2 that's coming into our compressor. We know it's saturated vapor, and so what we can do is we can look up the properties of saturated vapor. It's at low pressure, the 1.064 bar, and it's at 248.15 Kelvin. So again, since it's saturated, we could use our saturated tables from our textbook or reference book, or we can go to the NIST chemistry website, webbook, and we get the enthalpy. H2 is 383.45 kilojoules per kilogram. The entropy of that stream is 1.746 joules per gram Kelvin. The NIST chemistry webbook, remember our units for entropy are joules per gram. And again, with MathCAD, make sure you're aware that GM is the unit for mass. If we have isentropic operation, we just set S3 for the isentropic case equal to S2. So S3 is 1.746. So now what we have to do is we have to find the temperature at which P3 is the high pressure, because this is coming out of our compressor. So 6.8543 bar. And we need to find where our entropy is also 1.746 joules per gram Kelvin. Another good thing to remember is that this is going to be a superheated vapor state. And so if you have access to superheated property tables, you can use that. You could also use pH or TS diagrams, but those are often a little hard to read and not very accurate. So I would recommend that you go to the NIST webbook, and after you type in, of course, the R134a, then we know the pressure, right? We know the pressure. We want to find the temperature where we get this entropy. And so I would select the isobaric properties, enter P3 for your pressure, and then what you'll need to do is, with this web book, it generates basically a table with a temperature range that you specify. And so we can enter a wide range and then narrow it down if we want to. And so we know that TH is 299, or about 300 Kelvin. And we know that T3, it's a superheated vapor, so it has to be higher than 300 Kelvin. So what I did is I started at 290 and I put 320 for my upper limit of temperature and used 1 Kelvin, 1 degree increments. And after looking at the table that was generated, I saw that I get an entropy of 1.746 somewhere between 308 and 309. So then what I can do is I can go back, and instead of entering 290 and 320, I could enter 308 and 309 with, say, a 0.1 degree C or Kelvin interval. And so I was able to do that, and I see that within 2 to 3 decimal points, I have an isentropic temperature of 308.1 Kelvin. And then I can read off the isentropic enthalpy of that superheated vapor as 421.97 kilojoules per kilogram. And then I've just entered my compressor efficiency here since I forgot to enter it up there. So now I can calculate the isentropic work. The isentropic work is the isentropic enthalpy of stream 3 minus the enthalpy of stream 2. And the isentropic work ends up being 38.52 kilojoules per kilogram. Now I have to factor in the work, the efficiency for the work. And so I do that by, since this is a compressor that's requiring work, the real work is going to be larger than the isentropic work. And so I need to divide by the efficiency. And I get the real work is 48.15 kilojoules per kilogram. Now ideally I'd like to have this in kilowatts or watts, but we do not know the mass flow rate of the refrigerant in this cycle yet. And so I have left this just on a mass basis. So now that we know the real work, we can then go ahead and calculate the temperature of our stream 3. So we do that from our energy balance. And so remember, our energy balance is work is equal to delta H. So now I have the real work is equal to the real enthalpy of stream 3 minus the enthalpy of stream 2. And I called this, I should just get rid of this typo. This should just be H2 because it by definition it is a vapor. So H3 real, I just rearrange H3 for the real stream, enthalpy of the real stream, is the work plus H2. And so I get a value of 431.6 kilojoules per kilogram. And so now I need to go and I need to find the temperature at which that is true. So the pressure is the high pressure, the 8543 bar. Get back down here. The pressure is 6.8543 bar. The enthalpy is 431.6. So now I need to find the temperature at which I get those two conditions. So I go back to the NIST page, I enter my pressure, and then I enter a temperature range. And so if I figure it out, the temperature range the temperature has to be higher than the isentropic temperature, right? And I went ahead and again, I believe I just used a 290 to 320. And if you go back through there, it's somewhere between 317 and 318. And then again, I can refine my search using a smaller interval. And I find that to 1 decimal point, T3 is equal, for the real case, is equal to 317.8 Kelvin. So now I have stream 3 fully defined. Once I have stream 3 fully defined, I can then move to the condenser. Now, the important thing to realize about the condenser is that we are doing a cooling process that we need to think of in 2 steps. We are taking a superheated vapor, stream 3, and then we're condensing it. So the 2 steps that are involved when you think about modeling that thermodynamically is we take our superheated vapor and we cool it down to a saturated vapor. We cool it down to a saturated vapor. That's going to go from T3 real, which is 317.8, to Tsat at our pressure of 6.8543 bar. That step is called the sensible heat most of the time when you see that in textbooks or in the literature, because that's the cooling is accompanied by a temperature change where you actually feel, you could, if you wanted to, you could feel that refrigerant cooling down. To condense it, we then have to take that saturated vapor and condense it to a saturated liquid. Now remember, that is a phase change, and that is going to occur at constant temperature and constant pressure. So at Tsat and Psat, which is the 6.8543 bar, we will have that phase change. That is the latent heat, and that is related to the that is equal to the delta H of vaporization for that refrigerant. So we've got two steps: sensible heat and latent heat. For the sensible heat, that is equal to just Q is equal to Cp delta T. So we need a heat capacity value. So what is a heat capacity value? Well, if you go and you look at the property tables, we are going to be cooling from 317.8 down to Tsat, which is TH of our evaporator, right? So we need to figure out what heat capacity value we should use if we have our fluid going from that temperature, T3 real to TH. And if you look at the property tables, and again, this is why I like using the NIST webbook, because all of these are conveniently in one nice resource. We don't have to go through page through other books and reference sources to find these. What I found was at 317.8, it's 1.03, and then it is 0.99. So it's relatively constant, but yeah, there's still a little bit of a change. And these properties are so easy to look up. What I decided to do is just take the average. Take the average at the high temperature and the low temperature, of the high temperature and the low temperature. And so we get a value of 1.014 joules per gram Kelvin. Again, make sure you're careful with the units that you read from these tables. So now that we have our CP, we can calculate the sensible heat contribution that's going on in our condenser. And so that's just Cp delta T. And so delta H for the sensible heat transfer is minus 18.9 kilojoules per kilogram. Should it be negative? Yes, it should, because we are our system is our refrigerant liquid, and we are giving off heat to the environment. So we are losing energy. So that should be negative. Now we have to calculate delta H of vaporization, the latent heat. And this is going to be at Tsat, which is 299.15 Kelvin. So what we do is we go to our property tables and we look up the enthalpy of saturated liquid and the enthalpy of saturated vapor at 299.15 Kelvin. Again, you can use either textbooks or you can use the NIST chemistry webbook. We get these values. We subtract one from the other. And remember, we are going from vapor to liquid, so our delta H is liquid minus vapor. And that is minus 176.87 kilojoules per kilogram. Another thing you can do to check your answers to make sure that they're at least thermodynamically consistent is take a look at these values. In almost every case that you will deal with in practical situations, latent heats will be much greater than sensible heats. And that's because so much energy has to go into or be taken out of a system that's undergoing a phase change compared to the amount of energy that is needed just to raise or lower the temperature. And so we see close to about 9 times greater. That makes sense. Also, we've got our sign right. It's negative because our system is being cooled and given off energy. So we sum these up, and this gives us our QH value. Now, your textbook in the example, they did not ask you to calculate QH, but I wanted to do that anyway as an illustration. So QH is given as the sum of our sensible and latent heat changes. And again, this is a negative value because we are rejecting heat from our system to the surroundings. So now we have the condenser worked out. The last step that we need to work out is the expansion valve, or the throttling valve. So as you remember, a throttling process, the energy balance reduces to delta H equals 0. It's isenthalpic. There is no work being done. There are no changes in kinetic or potential energy that are significant, and we're also assuming that there's no heat being given off. So that's what our energy balance reduces to. Since stream 4 is a saturated liquid at the high pressure, we can assign the value from stream 4 from what we looked at above. That is just simply the enthalpy of our saturated liquid that we used up here. So that's 235.97 kilojoules per kilogram. That is the enthalpy of stream 4. So now we apply our throttle energy balance, and we get that, I forgot to bring this over, that is H1, enthalpy of stream 1 coming out of our throttle valve is equal to the enthalpy of stream 4. So that's 235.97 joules per kilogram. And so what I'm going to do right now, I'm going to do another extra calculation. What I would like to know is coming out of that throttle valve, if we go back up here, remember coming out of that throttle valve, it's going to be a mixture of saturated liquid and vapor. And so what I would like to calculate is what is that fraction of liquid, or what is that fraction of vapor. And so I can do that because I know the pressure of stream 1, I know the enthalpy of stream 1, I also know the temperature, right? That's Tsat. And so what I can do is I can look up in my property tables, I can look up the enthalpy of saturated liquid at T1 and P1 and the enthalpy of saturated vapor at T1 and P1. And this is what I get, and you can see that my value of stream 1 is actually in between, which is exactly what we'd expect for a mixture of saturated liquid and vapor. So once we do that, we can then calculate the fraction of liquid, the fraction of vapor, using the quality calculations that we had back in chapter 6. So the fraction of vapor ends up being 31.8%, and then by definition the fraction of liquid is going to be 68.2%. So that gives us our fraction of vapor and liquid that's coming out of the expansion valve. The rest, this vapor is formed immediately in the expansion valve. The rest of this liquid is going to be evaporating in the evaporator coils. And by the time our refrigerant comes out of those evaporative coils, we are assuming that it's completely evaporated so that our X1 vape is equal to 1.0 or 100%. All right, now that we have all that done, we can start to calculate a few other things. So we were actually told what the refrigeration capacity was. It was 120,000 kilojoules per hour. This, by the way, is what QC is, right? The heat that's absorbed in the evaporator is QC. And so you can leave it in kilojoules per hour, or you can convert it to kilowatts, and we get 33.33 kilowatts. Now what we can do is we can use this to calculate our mass flow rate of the refrigerant, because this is what is going to determine if we have to have 33.33 kilowatts of refrigerant capacity. That is how we are going to figure out how much refrigerant has to be in our system. How big does this refrigerant have to be? Is it 1 kilogram a second, 0.1, 5, 10? What is it? Well, to do that, we do an energy balance over our evaporator. And so, again, our evaporator is operating under steady state, so there's no accumulation. So accumulation is equal to 0. What's our input minus our output? Our input is H1, is stream 1. Our output is H2, which is, again, I have H2 vapor. Let me just make this consistent. H2, all right, our saturated vapor. Do we have any heat being transferred? Yes, we do. We have QC being absorbed because we have evaporation going on. So that's positive QC. Do we have any work being done in the evaporator? And the answer is no. We do not have any work being done in the evaporator. And so what we can do is we can take, this is our energy balance. And we can take this and we can solve for the mass flow rate of our refrigerant. So we solve for the mass flow rate of the refrigerant, and we get a mass flow rate of 0.226 kilograms per second, or 813.67 kilograms per hour. So now we know the mass flow rate of our refrigerant. We can then clean up some of our calculations. If we wanted to convert all of our work in our QH values from kilojoules per kilogram to kilowatts, we can simply take those values and multiply them by the mass flow rate. You can see we get these answers here. So our compressor, 10.88 kilowatts, that's a pretty good size compressor. And our heat transfer, or our heat rate that is rejected to the warm environment, that is 44.25 kilowatts. And again, this is a negative sign because heat is going from our system to our surroundings. So we've satisfied the calculation for the mass flow rate of the refrigerant. We can now calculate the coefficients of performance. And so the coefficients of performance for a Carnot cycle, if this refrigeration cycle were operating via the Carnot cycle, which remember is theoretically impossible, but it gives us our upper limit for the coefficient of performance, we just simply use the temperatures. Tc over Th minus Tc, because the Carnot cycle is independent of the fluid, and we get a coefficient of performance of about 4.866. We can also calculate the coefficient of performance of the real cycle, and that is defined as the heat that's removed, QC, divided by the work that's put into our system. And so to get the units right, I put everything in kilowatts, and so we get a coefficient of performance of 3.063. And as another check that you can do as you solve these problems, you can look and make sure that your real coefficient of performance is less than your Carnot. That checks. Also, as you'll find, most coefficients of performance are usually somewhere in the range of maybe 2 to 4, maybe up to 5. But for most heat pumps and refrigeration cycles, you will see COPs right around 3 to 4. The other thing that I wanted to do is let's just check to see. Remember, our refrigerant is a closed system undergoing a cyclic process. Now we've got little unit operations in our process. We've got a compressor, we've got a condenser, a throttle valve, an evaporator. Those are all, if we take each one of those little unit operations at a time, those are open systems. But our refrigerant that's going through the cycle, remember, that is a closed system, because we start at any point, and by the time we get around to that point, again, we should be in the exact same state. So what I wanted to do is I just wanted to see if first law is satisfied in this process. So remember, the first law, our energy balance for a closed system is delta U is equal to Q plus W. So what is Q equal to? Well, Q is equal to our QC and our QH. So we simply just add those together, just keeping the signs. Don't make any other changes. Don't change the signs. Just use what you calculated. And then we add the W, the work input. That's the only work that's involved. theoretically this should equal 0, right? Well, if we do the calculation using the numbers that we did here, we get a value of minus 36 watts. That's not 0. What's going on here? Well, this is actually pretty small. I mean, you look at the QH, you look at the QC, you look at the work that's involved. This 36 watts is about 1% or even less than that, close to 0.1% of the heats. And so this is not technically adding up to 0 like it should, but remember what we are doing. There are some round-offs that we used. Also, we are using property tables. These property tables are taken from experimental data. While we still have several decimal points that are being used in these properties, remember that the accuracy is probably plus or minus 5% or so. And so if we do these if we compare our calculated delta U to what it should be, and with respect to our QC, QH, and W, we see that it's less than about 1% error or 1%, and so that is probably why we are not getting 0.00000 for our delta U. So for practical purposes, we can conclude that the first law is satisfied for this. This is just this residual amount is just due to some round-off errors that are most likely present in our property tables. So that's a refrigeration cycle. One of the things, again, that I would encourage you to do as you work this problem, make sure we only had one copy of this on the first page, but I would encourage you to keep this figure to help you step through the process as you work the problem. Another thing that I think is important, of course, once you identify the temperatures that you're going to be dealing with, that tells you the pressures you're going to be dealing with. Remember, this is your high pressure side. This is your low pressure side. Once we know the temperatures and pressures, we can then make a little stream table. And so it's difficult to make tables in MathCAD, but we can organize our information. Make sure you're careful with your variable names. Organize your material, your information, so that you keep track of what you're dealing with. Then, like I said, you have a couple options to start the calculations. Make sure you start at a place where the degree of freedom is equal to 0. In this case, we could have done this at either the compressor or the isenthalpic throttling valve. And as we go through, we just divide and conquer. We take one unit operation at a time. We start with a compressor. We've done compressor problems now for several weeks. We then go to the condenser, realizing that there's a two-step process for cooling: superheated to saturated, saturated vapor to saturated liquid. We then go to the expansion valve. In this case, we did the extra calculation of the amount of vapor and liquid immediately coming out of the expansion valve. Once we had all that information, we could then finish up and solve the problem.